All right, so this is what we're going to talk about today. We've got a lot to review, and most of it is on video. So with no further ado, let's get started. I'd like to introduce Richard Kalasa, Technical Sales Engineer with WL Plastics. Richard is a common speaker with the Alliance. So Richard, thank you for being here today.
Good to be here, Peter.
Alan Ambler and Ian Detloff coming from Dayton. I believe Stephen Boros from Pipeline Plastics will be here. And then, of course, John Stevens, Dan Land, and Brian Swanson from our team. Welcome, Alliance team. We're ready to go. So if you want to take a snapshot, you want to contact any one of us, take a quick photograph of this screen. All right, so let's take a look at this. What is butt fusion? The magic starts here. It's not magic, it's not voodoo. It's actual science. This beautiful resin can be reheated multiple times to create what we call fusion.
Go ahead. I have to set it backwards. That was pretty nice.
So there is both an interior bead and an exterior bead as a result of this fusion. And Richard, what impact does that interior bead have on the performance of the flow?
It really doesn't have any. When the hydraulic testing was conducted on polyethylene with the bead inside, the Hazen-Williams factor did not change. There has been lots of discussion around turbulence in these internal beads, if there is any. More so on a gravity system than a pressure system, it really doesn't apply. But when you get into larger diameter pipes, those beads can get fairly large. And so for a sewer or gravity system, you may want to consider those for slow or low sloping grades, such as 2 to 3%. In a sloping grade, to remove them just to stop any kind of buildup in that area. And again, high velocity events in a gravity system, those will just wash out because nothing really sticks to polyethylene.
All right, so in this illustration, we see this guy up in Austin, Minnesota. This is a city that only uses polyethylene. We like to say clean it, shave it, heat it, fuse it. And he's demonstrating what one individual can do all day long. Key terms for us to pay attention to are facing, another word for shaving. The heat soak is when that heater plate, we see this right now, that heater plate is soaking heat into the pipe ends. Now we're into the open close. So we open it, we inspect it, we pull out that heater plate and we stick it together. That's called the open close. Now we're in the fuse cool. We've fused it together and now we go through our cool cycle. So here's a close-up of what that heat soak looks like. The heat soak generates a bead. It's also called bead up. And here we have Macalc, which is an app, which if we're not using a data logger, we can use the app. And the app tells us what all these times are and what all these pressures are in order to effect a proper fusion. All right, we have another type of fusion. Let's listen to Andy Carr from George Fisher talk a little bit about electrofusion. Andy, let's look at one more on here.
Yeah, so this is a electrofusion corporation stop saddle. This is a very popular product as well. Historically, corporation stops have been used on the mains to tap them for your service line. So what we've done is we've developed a saddle that basically you can screw your corporation stop into if that's the way you want to go. You don't want to use our electrofusion tap tees. Basically, you would fuse this to the main just like you would fuse the previous saddle we talked about. And then you would screw your corporation stop in there and your tap machine would hook up and cut through the corporation stop.
What if I don't use that kind of thread?
That's okay. This is a CC thread for a corporation. We also offer female iron pipe threads as well. So a lot of times for air release situations and forced sewer, they'll have a male iron pipe nipple, if you will, that would go in there as well.
Okay, so we have the same program going on underneath this one as well.
We do. Yeah, the same procedure. Absolutely.
So we've got a copper wire, got a cold zone, a hot zone, and a cold zone.
Correct.
Yeah, great. Okay, so that was Andy Carr with George Fisher talking about electrofusion. Now,
Hey,
go ahead.
Can I interrupt you? I just want to, there's a really cool question that came from Mike Detherit, I believe. It said, is there a guideline for clearing to implement along a high density pipeline installed on surface of the forest area susceptible to catastrophic wildfires? This is actually a good question because we did have that event occur in California where the pipe melts. So first and foremost, polyethylene is a hydrocarbon. It will burn. Okay, so and it'll burn very clean because it's just hydrogen and carbon. But however, it will burn. There really isn't any prepping when you lay a pipeline on the surface. After the fires in California, we did some studies and looked at how hot the ground got in those fires that occurred. And really, the only first 8 to 6 inches did we see any temperature increase of the ground in there. So the best solution for any high density polyethylene pipeline is to bury it. And it doesn't have to be a deep burial, it just needs to be a shallow burial. Anything around it, like if you had leaves or forest, any kind of flammable item that comes up from falls or winter leaves, whatever the case may be, it'll burn, but so will polyethylene. So there really isn't any prep. Could you coat it? Could you case it? Yes, but that would still get very, very hot in that surface. But so it would probably get close to a melting point where it could affect the performance of the pipe. So there really isn't any clearing preparation for surface. You just have to be aware of where it is. If you're going to put it in anything away from forest, whether it's a cut line or whatever the case may be, that may be the best, but the environmentalists might not allow for those clearings to occur. So you just have to be aware and cognizant that if there is a fire there, that pipe is susceptible above ground.
Thanks, Richard. Okay, so in butt fusion, we say clean it, shave it, heat it, fuse it. In electrofusion, we say clean it, peel it, clean it, fuse it. There are two cleans. And this is what a peel looks like with a buried pipe. So this guy's preparing it for a saddle. He has to do a full circumferential peel if he's going to follow the proper MAB guidelines. And we do recommend that you do that. Then on this video, Richard and I were here in upstate New York. This guy is peeling the end of the pipe. This is going to go into an electrofusion coupler, and you are permitted to, quote unquote, finish your peel with a hand scraper. And tell us, Alan, why is he cleaning the inside of a bagged coupler?
He's making sure that anything that might have otherwise been contaminated in there has been removed through that isopropyl alcohol that's going there. We just want pure resin, Pete. We're just letting all that HDPE resin merge between the melted surfaces and do that. So any type of fusion we've got, and we've got a great question. Pete, I would like to give you an update that we've had 8 questions in the first 10 minutes with multiple follow-up questions, so this audience definitely gets it. Thank you all for thinking through everything as well. There's prep that's different with butt fusion than it is with electrofusion. Both techniques all get us down to that virgin resin material, and we're simply melting it to the proper temperature and allowing that interface to flow those molecules across. Now, when we're looking at any type of deviation, as we had a great question here in size for butt fusion, that fusion machine faces that. It removes the material, so that way when we push that together, it's nice and flush. In the electrofusion, we're doing that with the peelers and the other things that we're doing it. So there's just a little bit more of the operation step. Great questions out there. We're answering it as we go through. We had one for anchor blocking, which we'll get to a little bit later, Pete. So keep going. You're doing great.
All right. And so what we notice here is this guy is pounding on the MJ. You don't want to pound on a coupler directly. This mechanical joint adapter has already been attached to the spool piece. And then you'll see that as he's banging on it, he's got a witness mark right here. And that's how he knows what the stab depth is. How far do I have to stick the pipe into the coupler to make it work? Well, he did his math, did his geometry ahead of time, and he marked it so he knows how far to stick it in. That's called a stab depth on an electrofusion coupler. So send your questions if you have them. All right. Now we're going to move into seismic performance. Why seismic? Because ground movement is the #1 reason older pipes fail. And the cool thing about polyethylene and ground movement is We move with the ground, we don't fight it, and we don't get damaged as a result of ground movement. How do we know? Because we're going to watch this video. So here we have some humans for scale right here. Tom O'Rourke at Cornell University built this trench box to simulate polyethylene on a fault line. So polyethylene is running in this direction, and the trench box is moving in this direction in order to attempt to damage the polyethylene pipe. And then we see same moment, same movement, different camera. Richard, tell us what's going on here.
Yeah, so what you're seeing here is the actual movement of the polyethylene. So you're just witnessing the ductility of polyethylene. In this particular case, what the big surprise was in that 4-foot movement that he did move with the sensors and everything, when they started to de-earth the pipe itself, it actually wanted to move back into its original straight line position, meaning that it's kind of in the viscoelastic behavior zone, so below the tensile yield stress of the product. So it didn't thin the walls, it didn't deform the pipe at all, but it actually wanted to come back to its original form and size. So in this particular case, if you had any kind of seismic event or ground movement in this case, with polyethylene pipe, you can maintain your fire system, if this is a fire system or water system, to that area, especially in a critical situation like an earthquake. But also, if you're just having regular earth freeze thaw cycles in your ground, you're not worrying about your joints separating and anything else and causing these leaks that occur in a lot of municipality systems today.
Thank you, Richard. Napa, 10, 11 years ago now, also had an earthquake. So we go from the theoretical to the actual. They had an earthquake. I was there 3 days after it happened. I interviewed the engineer, and she told me that she had a lot of breaks. It took them 6 weeks to get that system fully operational. What I didn't know at the time is that Napa Sanitation had been using poly for 30 years. It's now been 40 years. During that earthquake in 2014, Napa San went back to work as normal. None of their 30 miles of polyethylene had any damage. Yet their sister agency, Napa San, had a lot of damage, but they didn't use polyethylene. They used ductile iron and PVC. One agency uses it, one doesn't. One went back to work as normal, one did not. I let you make your own opinions of that event. Recent earthquakes, implications for U.S. water utilities, published by the Water Research Foundation in 2012, determined that these 3 huge earthquake events, 4 6.0s in Christchurch, one 8.8 down in Chile, and a 9.0 in Sendai, Japan, known as the Tohoku quake, no polyethylene failures occurred as a result. And all of these areas used polyethylene extensively. So we have the theoretical, we have the actual. Polyethylene, when the ground moves, does not get damaged. That's not to say you can't scrape it. Take a look at what this guy did in outside of Dallas in a suburb. He fused up the polyethylene in a nearby schoolyard, dragged it 4 blocks on a road that had not been swept. He didn't use pipe rollers. He didn't use bales of hay. And look at what he did. Alan, is my pipe damaged?
Well, it sure looks so, Pete, but it's not beyond that 10% wall thickness that we're talking about. So there's an allowable gouge of 10% of the wall thickness. It is very common to drag this pipe over top of the surface, and all you're seeing happens to be one of the beads that's been scraped off there. Now, if we did have a gouge, Pete, we're going to do what's called when in doubt, cut it out. If we don't know whether or not that exceeds the 10% allowable wall thickness, and we'll cut that section out. And that's one of the beauties of the durability and ruggedness of HDPE is we can simply redo that fusion in the field. Great question, Pete.
All right, here we have another way to move a pipe string. Here, this road has been swept. Alan, this is one of Alan's clients out in Napa, California. Alan, tell us what's going on here.
Yeah, sorry, Pete. I was trying to answer a question for us there. We're simply moving this from the laydown yard, which is about less than a mile away from the project. This is in Napa San as well. If you guys can look pretty closely there, you'll see Dan feverishly running behind the pipe string as they're doing that, and the construction crew was laughing at him as they moved through there. But we're dragging this across the surface, and it doesn't take very long to move it from the laydown yard to where we're putting it in. So we're really not seeing that much of an impact to traffic in the area, and that whole process doesn't take very long to do the pipe bursting either. So we're certainly minimizing the amount of impact that we have on the neighborhood in the surrounding traveling public.
Yeah, Alan, I have heard contractors and owners complain about the extensive laydown area needed by polyethylene. Unlike PVC, PVC, you can have a smaller area, but our laydown areas are longer, but they're very short duration. Am I right?
That's correct. So the actual act of pipe bursting 500 feet, you could take an hour to pay out the rods or cable through it and then turn it around and come the other direction in static, and that could take an hour as well. So we're really not impacting that community for that long. HDD sometimes, obviously, when we've got larger pools, that's going to take a little while to do it, but most of the actual install is pretty quick when we can get it done.
Awesome. Wow.
This looks pretty severe, Pete.
Well, I've heard for years, Alan, what they do in the mines. I'm not an expert in the mine market, but when I found this video, I couldn't believe the way they abuse the polyethylene. Richard, is this pretty common in the mining market?
Absolutely. These guys have kind of taken on their own specifications on handling and rough handling because they used to use steel and aluminum pipe where they couldn't move it at all. It would take literally days to relocate to a different location, whereas now they just drag it along and they find that if there is damage to it, then they replace it, and they understand that there is a limitation. But yeah, this is severe. This is severe rough handling. I wouldn't call it best practices, but again, polyethylene's tough, but it's not indestructible.
There's
And
definitely
they make
not
it
an
look like it
ASTM
is.
standard for this, Richard. You're right
Yeah,
about that.
there's no ASTM standard for that one, unfortunately. But they get it. They understand it.
All right, now we talk about the data logger. For those of you that watched the pre-show video, the data logger is a really important tool that engineers can use to make sure the pipe's going in the ground and the fusions are occurring the way we want them to. So we have a quick illustration. You got to key the data into the data logger, but let me stop this thing right here. So what's occurring? This is reading pressure over time. So right now we're at 1 minute and 20 seconds over here. We started at 84 PSI. It jumped up to just under 168. This is the initial beat up, or when the pipe, the heater plate is coming up against the pipe. That's the initial, what we call beat up. And then you want to drop your pressure to drag, which is what this is. So it dropped from here all the way down to here. So we're learning how to read this data logger report. And now we do the heat soak. So we're soaking heat into the pipe ends from here all the way through here. All right, so now what's going on here? This is heat soak. We're watching a bead grow from here. It's like molasses, right? Sometimes you don't see it. Walk away for 30 seconds, you'll see the difference. Then we have the open close. So open close is we pull that heater out, we look at it to make sure there's no foreign substances in there. And then we stick it together under pressure. Now our pressure spikes from drag pressure all the way up to here. And now we move into the fuse cool cycle, which is prescribed at 153 PSI for 4 minutes and 17 seconds. This data logger report can actually serve as a quality control device, even though you're not there. It's being done every day. We've had millions of these reports submitted to McElroy's Vault. Really pretty cool system. I'm a big fan. We talk about it a lot. We encourage you to use the data logger and ask for it. So as part of the process of, go ahead.
Peter, yeah, so just to add to that, in that cooling section there, you're going to hear about rough handling. And so that cooling section after the heat soak is finished and you're putting pressure on the pipe to cool, right there where it starts, that time is really set for the different DRs. Yeah, different DRs and thicknesses, because polyethylene has a very good thermal insulation factor. So it wants to retain that heat. So we want to make sure that you're in the solid phase all the way through that wall. And that's why that these graphs are so nice, because it confirms that you've met that. And then any rough handling after that in the procedures will be applicable after that cooling point. So it's really critical there, because we've seen people try to save time because it looks cold. But if you've ever been to one of the A shows or demos that Peter conducts, you'll feel the fusion joint. It's not that warm as soon as he pulls it out, but then it gets warmer and warmer and warmer because that heat continues to come out of that joint. And so you want to get to that solid state. And that's where that chemical bond and that interaction of the time molecules really occurs. So that joint is really not a joint. It's basically becomes a monolithic system.
All right, to give you a little more on that. So according to this, the 3/16 inch bead cools for 4 minutes and 17 seconds. And as Richard says, in addition to the 417, we have a 30-minute rough handle time. So you're permitted to pick up that pipe, lay it on the ground, move it 50 feet, put your next joint in. That does not violate the rough handle rule. But if you drag it anywhere else, if you beat the heck out of it like they did in that mine image, you're violating the rough handle requirement. So the standard doesn't really do a good job defining rough handle, but just think of it like a jelly donut. That jelly donut, it's soft in the middle at the end of fusion, at the end of fuse cool. And then once we get through the rough handle, it's really hard. That jelly donut is solidified. So we want that jelly donut to do its thing.
I hadn't heard the jelly donut one before, Pete, but you're right. The standards don't do a good job, but that video sure showed you what rough handling really is. So
Yeah.
after you work with this stuff in the field a little bit longer, everybody out there, you'll figure out how far the HDPE can go.
All right, we got a lot of questions about bead trimming, and we have Jesse Salisbury to thank. He's a member of the Alliance, and he attends a lot of our events. Let's take a look at what an interior bead trim looks like. What are these little antennas?
This will actually retrieve the bead, and so you'll have it in hand when you remove it.
All right, and the fundamental elements are the cutter, which is right here.
The
What
cutter,
else?
and we have an adjusting nut right here, so we can adjust the arms and the index wheels on this. I slid it so that the index wheels are right up against the bead. That's perfect alignment so that our cutter is perpendicular to the bead itself. I did a quick counterclockwise turn to engage the cutter, and then it's a full revolution around. Yes, thank you. And usually what you're doing is you're doing this on the machine, so the bead's a little bit warmer.
This is what a bead looks like. All right, so now you see what an interior bead trim looks like. And that is R&L Manufacturing bead trimming tools. You can get those wherever you buy your polyethylene gear. We also have products that can remove the exterior bead. Alan, why might we want to remove an exterior bead?
Well, for slip lining applications, Pete, or compressive fit slip lining applications, when we're going to put it into a pipe, an existing pipe where we do not have that much annular space surrounding the pipe for slip lining, in compressive fit slip lining, we're using that technology to take the OD of the HDPE, temporarily change its shape to make it smaller. Then we're pulling that into a pipe and then allowing that one to relax. So while we are changing the shape of that pipe, we're pulling it through a reducing die or series of rollers.
Okay.
We can't have a bead.
Sean
on the
is out here
outside,
with
so
me,
that's
and
it.
we're going to do a new. Thank you, Alan. Sorry about that. pneumatic bead trimmer on this same 20-inch pipe where we demonstrated the fantastic McElroy T900i. And this bead we made, I think we made this one 2 days ago, so it's probably a pretty cold bead. Tell us about the equipment that you have and how it works.
Okay, so this is the universal external bead trimmer. Recommend from 12 inches on up. There's a couple different techniques depending on the size of pipe that you are going to be debeading.
Okay.
And I'll try to show you as I'm doing it the best that I can. And so I guess this.
And you hook, and you got it. What kind of airflow do you need? It's
so
pneumatic.
It's pneumatic. It's requires 8 CFM, about 90 psi.
Got it.
And so pretty standard for any shop air compressor.
Good. Well, let's do it. All right. Okay. Camera 3 needs to get up tight on this. Take it away, and I'll stand back. And you, remember, the camera's behind you, right?
Yeah.
So you got to move the camera so that you can get in, so you can see it. All right, now we're going to do the back side.
So that one was more for like smaller diameters. If you're going into a bigger diameter pipe, the other way would be to kind of break it, and I'll kind of show you right here. You kind of make all these little steps, and then kind of take it away a little bit.
All right, you get the idea on bead removal. We'll show a couple more videos later on when it would make sense to do that. Alan, tell us a little bit about the Plastics Pipe Institute and the great work they do and how and why they come up with technical notes like this one.
Okay, great. So they are a research organization and general information warehouse with lots of great individuals that are working together within the polyethylene industry to put forth the best foot forward for technical notes, technical reports to be able to provide guidance on how to operate HDPE, install it, and maintain it and test it as well. So a lot of that information came from the natural gas distribution side of it. So then the tolerances and the importance of not failing is significantly higher there than it is for potable water, because the impact of failure in natural gas distribution has a much higher impact. So this is actually from the natural gas distribution side, where they're going to squeeze off that tool. They have a tool that squeezes off that pipe. So if we have some type of a gas leak in a lateral or something like that, then we'll simply squeeze that off, and you'll see here. Keep going, Pete. I'll just talk a little bit over it right there.
Hey,
We've heard you talk about it before.
After we do this, can we do our question for our audience?
Yeah, absolutely. I'll load it up.
Hack. Today we're here to demonstrate the Footage, that's the brand, squeeze-off tool is the process. So the Footage squeeze-off tool. And we're going to do a 4-inch DR17 squeeze-off. But first, let's get to know the gear. Bob, tell us about this piece of equipment.
All right, so this is a Footage combination screw and gear-driven squeeze-off tool that will accommodate 2-inch to 6-inch pipe. Today we're using a 4-inch DR17.
Let's take a look at the front of the machine.
So this is the screw drive and this is the gear drive. The gear drive gives us more torque for a pipe with a thicker wall.
So this, Bob, this does 2 inches to 6 inches,
correct,
right? And how do we switch from one to the other?
So this dial will adjust to accommodate whatever diameter and DR that we're squeezing off.
So we love squeeze-off tools, and the cool thing about squeeze-off is the fact that you can fully stop the flow in a polyethylene pipe. Go ahead, get started, Bob. And the thing about this is we learned this process was initially developed for the natural gas distribution market. And it's just starting to be used in water. But when you don't have a valve and you've got polyethylene pipe, what a great way to stop the flow. So in the natural gas markets, repair trucks, they all have these on their trucks. They don't have the 30-inch diameter ones, but they certainly have the smaller diameter squeeze-off tools that are immediately available when they pull them off the truck to go into the trench. So Bob, what are the rules for squeeze-off on a 4-inch DR17?
Well, the Plastic Pipe Institute has given us guidelines that say the general guideline is 1 minute down for every inch of diameter of pipe.
Okay, so for a 4-inch, it's 4 minutes down.
4 minutes down.
And then on the release, what do we do there?
8 minutes back.
Okay, so 4 minutes down, 8 minutes on the release. If it's an emergency and you have to go super quick, go ahead. You're not going to kill the pipe, but just know that you may have damaged it. So then either drop in a spool piece or grab a Hymax band clamp and put a repair clamp around the OD of that pipe, and you're good to go. But if you don't follow the rules, just treat it as a repair and you'll be fine. All right, so to be a little bit more specific, on a 4-inch 17, 2 minutes on the squeeze, 4 minutes on the release. So that general rule of thumb that we gave in that video is kind of inaccurate. It's a general rule, but if you really want to know what it is, it's temperature driven, and you have to look at the table published in Technical Note 54. Greetings, Peter Dyke here from... Okay, and now Footage has now come out with a 24-inch tool developed with ISCO, and that's the largest size available. I said 30 inches in the video, that was incorrect. 24 is the max. This is a very large hydraulic machine available for rent from ISCO. So back in the day, the guided side bend test was one way to test whether or not the Fusion Tech knew what he was doing. This image on the right is an example of what not to do. Let's take a look at a video. Greetings, Peter Dyke here from the PE Pipe Alliance. My colleague Bob Hack and I are going to talk about McElroy's side bend tester today. You know, for years we've talked about the importance of accountability on the job site. The importance of that engineer knowing that the polyethylene project is going to be handled in the manner that she intended. Well, we have the side bend tester. This is a destructive test that can be done in the field by the inspector or by the contractor for review by that inspector or that engineer. Bob, tell us a little bit more about the process.
All right, Peter, this is a cross-section of an actual fusion that was done in the field. It is run through a planing device, and we're going to place it into the side bend test machine where a piston is going to press down on that joint to validate the integrity of that fusion.
You know, this is really not only a very cool process, but this is side A, this is side B, this is where the fusion occurred. And you know, looking up close, you can't even tell that a fusion occurred. And that's the beauty of the polyethylene thermoplastic pipe, Bob. But another thing is, once we put this through, if we were to hear a crack or see a tear, we'd know that the operator probably didn't do his job correctly during fusion. Let's take a look at the machine.
All right, so this piston is right down on top of that fusion joint. And the gauge on the front of the machine here is showing us the degrees to which we're going. We're going to take it up to 90 degrees.
All right, let's release it and take a look at it. All right, how's that look, Bob?
No visible signs of any cracks. We didn't hear any pops during the process.
Yeah, there are no tears there. So this is a good fusion. So we now have confidence to know that that operator, that contractor, the sub, or the GC is doing the fusions correctly in the field. We see this on the first fusion of the week, the first one of the month, whenever they change operators, whatever interval the engineer specifies, this can be done. It's relatively inexpensive, so you can learn more about it at pepipe.org. Go to McElroy's website or talk to your favorite polyethylene distributor. Okay, so we have an ASTM standard for this as well. 3183-16 is the most current version of that.
Hey, Pete.
Yeah,
Hate to interrupt. We actually also have a specification for this in that package that we have for the specifications. That's part of the new update from last year as well.
Oh, nice. Good job.
Yep. So as we talk briefly, I could take over and launch the poll question, or if it's if
yeah,
you'd
go
like.
ahead.
Yep. Okay. So I don't know if you want to elaborate on some of this with Richard while this happens, but you'll have to enable some for me to take that over here. Hang on. I'll figure it out. Keep talking.
All right, and here's what that side bend tester looks like. We carry that on our truck. So
Yeah,
here's
and
another.
I do
Go ahead.
encourage people to ask questions. Like, there's no such thing as a silly question. So just ask us anything you want. We're really prepared. We're going to get to your anchor blocks shortly, but yeah, please keep the questions coming.
All right, so now we have a poll question. Thank you for that, Alan. What percent of construction is open cut? So that would be just general construction, not polyethylene. And what best describes your native backfill? We spend a lot of time talking about the soil profile at the Alliance. We have an ASTM standard for that. We have AWWA M55. Alan, could you give us the quick review of what soil profiles we're looking for in buried pipeline installations with HDPE?
Absolutely. So HDPE, like PVC and ductile iron pipe, are all considered to be flexible pipe materials with regard to the trench installation. So what that means is that pipe stiffness forms a interaction with the soil stiffness that's around it, takes any loading that's on top of that pipe, and then transmits it to the soil that surrounds that pipe. So there is a design window in the previous version of AWWA's M55 manual that shows that if you have a DR7 to DR21 with less than 25 feet of burial depth, but more than 2 feet for no H20 loading, or 3 feet for H20 loading, that's a box truck on top of it, then you don't have to do any calculations at all. If your loading is outside of that, the Alliance does have those calculators for you to be able to help look at the spreadsheet for it. But we're looking at the only soil that you wouldn't put back would be that class 5 soil, which is the peats, the moss, the organic materials, and all sorts of things. We do want to see some compaction associated with it, but HDPE has some, because it's fused along there, sometimes we don't have to put people back in the trench, and it makes it much, much more highly productive. So the poll looks pretty good here. Pete, you want to tell us what we've got?
I don't see the
Okay.
results.
We've got less than 50% here is 18%, 50 to 75% is 28%, 75% for that's the portion or percentage that construction is open cut is 49% of the install as well. What's the native backfill? We've got 28% that says poor, rocky is 11%, good is 53%, and ideal is 8%. So 8% say it's ideal. Great job, everybody. Thank you so much.
Hey, how many questions do we have so far, Alan?
Some of the great questions we've had so far actually go into temperature swings within the pipe, and then also restrained connections at buildings where we might be passing through there. For that's a hot water conveyance through that. We've looked at potentially being resources for local contractors, local municipalities that have adopted this pipe material. So we were asked that as well. The Alliance is particularly busy all throughout North America, so we oftentimes know who those local distributors, contractors, municipalities are that use this product. You are not the first. So if you're thinking that you're going to start your project and you're going to be one of the very first ones to do it, then that's not really the case. We have all those case studies for you. We've got all the good information for you in that manner, and be more than happy to help you realize that we've got all that information as well.
Thank you. All right, so here we thank the Discovery Channel for this one. Let's take a look. Okay, so Richard, tell me about the properties of polyethylene that permit him to move it around, but then when the bucket teeth get it and they move it onto rock, it damages the polyethylene.
Yeah, I mean, steel against polyethylene, steel is always going to win. Just because of the hardness. But again, that's just the polyethylene ductility. You got to remember this line is pressurized at the same time, and he's moving it around and bouncing it. And then when he pinned it, of course, it allowed those teeth to dig into the pipe. But you know, it's the all the curves from common hydraulics, like you know, if you have 90-degree elbows, it reduces that flow rate. But he got the tooth caught there, and the resistance was too high, so it just pulled it. But it's just its ductility. Polyethylene is just very, very ductile, and it's just a attribute that is so inviting to all piping applications because it can move. And if it is restrained by soils, that's fine. That's because you have that compaction, or your H20 or your E90 or E80 loads. I can't remember which they were, E80 or E90. But we don't have issues with that as long as it's properly designed for the crossing and the compaction of those soils around it. But it's ductile. I mean, that's just the best way to describe it.
All right, Richard, why don't you stay on? I'm going to run this video. We've got Chris Waite talking about coil pipe using what's called the line tamer from McElroy. Tell us what we're looking at.
Yeah, this is really important because whenever we coil polyethylene, this is a gas line, of course, so that's a medium density polyethylene. But whenever we coil it, sometimes when it's coiled, it'll hold a little bit of that memory for a short period of time. When we produce the pipe in a straight line, then what this will do is, as you're pulling that pipe out, it'll just give some readjusting, so to speak, for some compression and tension on that pipe to make it go back really quickly to its straight line. And you can see how straight that is. And once you release that pressure or that tensile force, it will remain straight. And that's a really excellent tool, especially when you're drilling. If you're drilling that, you can put it in. If you're laying it on the ground in open trench, then it'll just lay that thing out perfectly square for you.
Okay, so this item straightens the pipe and this rerounds it. So that tool is a dual purpose tool. Thank you for that. Okay, so we're not going to have the audio on this, so we can't run this. We can talk about this. So this is connecting to PVC. Richard, do you want to narrate what's going on in this video?
Yeah, sure. So they have to replace a joint there, a T, which was probably leaking. And of course, with PVC and ductile iron tight systems, they pour concrete around it to restrain any kind of movement that occurs for those more rigid materials. So they have to cut all that out, and then they cut through that and PVC, and then break off that T section. So then now what they're going to do is they're going to pre-make the transition. So it'll go in, put back on, and then MJ adapter back into the T. And I'm thinking because that's all polyethylene, they will probably add concrete around it, but they're also going to stick a new valve in it so they can shut that line off at that location. And so they're just prepping everything above ground with the MJ adapter into the valve. And again, that is fully restrained. You do not have to pour concrete over this valve section or that T section whatsoever. And of course, in operation, your temperatures will stabilize underground. And so there's not really any issue with expansion and contraction. And then they'll lower it down. We don't like to use chains, particularly. We like to use slings instead. Chains can gouge, again, steel against poly. Just best practices again. But, if you're conscientious of it and you do have chains, just put a little piece of rubber on the inside, between the two, and it'll be fine. So he's putting on the gasket now for the MJ. Nice and clean. Everything's will seal nicely.
We are working on getting the audio restored here, Richard, but you're doing great as a narrator. Absolutely,
Yeah,
as we see through everything.
Yeah, and then the bolts, of course, will all have torque ratings on them for that MJ adapter. So hopefully they're torqued in the proper manner so that it's even all the way around and that gasket is properly compressed.
Peter, you might have to reshare if it's not going to play the sound, but we'll check it. Play another video for us and let's see. Everybody, it's Nope, didn't have the sound. So try a reshare. It's 2:53, 2:55. So we still have everybody on the here through this. It is an open conversation. We've had lots of great questions, lots of follow-up questions through that as well through this process. That's what the Ask Me Anything panel is. And we're certainly very happy to try to continue to move this forward and provide you with as many images, as many videos, and all sorts of things that show these things live and running for you as we're going through. Here's a pressure test that we're looking at. And essentially what we've done in our McElroy area where we did a lot of demonstrations is we fused up a pipe run. We did put a service connection on it, so that way you could show how we do that service connection, and then also run disinfected water through that while we're disinfecting and pressure testing that pipe through it. We raise the one end in order to be able to release all entrapped air from that pipe. Air is compressible, water is not. So that's an important part of the pressure testing. We do have specifications on this pressure test for potable water applications and would be more than happy to be able to share that with you as you see it. But here we're simply purging the air out of this, conducting the pressure test. And you'll see that data logger that's right there. That actually has an adapter that will measure the pressure within the pipeline itself as we go through there. It's pretty cool. So we've got that attached to a small pump that has increasing the pressure through that pipeline, and then we maintain it. One of the nuance about HDPE happens to be that thermal expansion or expansion from Poisson's effect, in which case we will overcharge the pipe. So we're going to let it expand. Then we'll bring it back down to pressure test. So that's a difference of 5 or 10 PSI that we're looking at. And we'll hold that pressure test for an hour in order to be able to prove that it is in fact a leak-free system. If it was leaking, we'd see it right away as well. So here we go, Pete. I don't know what's on the next slide, but we'll certainly keep going. Lots of cool stuff for you here. These are tests that they perform in the facility itself. Richard, you want to come on and tell us what we're looking at? Okay, so what we're seeing here happens
yes, I do. Yes, I do. I apologize. Sorry, I'm just trying to answer questions at the same time. No, this is a pressure test. So for manufacturing, we have to pressure test all lots, all lines, all sizes. This is a very large diameter one, but you take it up to a pressure test within 60 to 80 seconds. You pressurize beyond the point of failure. And so what we're looking for is a very ductile failure. So in that picture right there, you just point at that split right there. It's called a fish mouth or very ductile. That's what you want to see. And what that means is that our extrusion process did not negatively affect the performance of the PE 4710 materials as we make it into a compound. So our heat process is a heat history. So we have to make sure that we're not degrading or affecting that performance in any way, shape, or form. And there are values for that. I don't know what size of pipe that was or DR, but there are values that we have to exceed.
That was a 10-inch 11, and this wasn't your pressure test. This was a pressure test to confirm that electrofusion coupler that is right here was done correctly. But it's the same functional test as what you guys do in the lab.
Exactly the same test. Yeah, you bet. So that's really good. That means it failed in the parent pipe. So the parent pipe is the weakest part of that joint for sure.
Yeah, George Fisher wasn't too happy here because I forgot I was supposed to fill the pipe up with water. I had air in it. So I basically created a little BOMB.
Do you remember the pressure rating?
So it was a DR11. So here's yours. Now you can talk to this one, Richard.
Yeah. So yeah, these are our tests. So anything, and you can see it expanding and blowing. That's a beautiful ductile failure. If you ever come to me, if anybody ever comes to me with this type of failure in the field, bottom line is you overpressurized it. That's all there is to it. There's no ifs, ands, ors, or buts. There's no other answer for that question. And that doesn't really happen very often. I have seen it in pressure testing above ground where the temperature got very, very hot and they didn't accommodate for the safety factor for that temperature rise. So it wasn't 73 degrees. It was more like 130 degrees. So it did fail ductile. So that's a classic example and a really beautiful failure. We love to see those.
Alan, did you want to add something?
No, no, I'm here to talk about the corpse saddle. You lead it, and I'll provide color.
All right. So this we got with, I should put Chris Wade from Secor on this one because he's the one that got me out on this job site. But this is a 10-inch polyethylene line with an Integrity Fusion Corporation saddle electrofused onto it. This is a charged line. So we're doing a hot tap on this self-tapping tee. Take it away, Ellen. It's not
So
a
the hot
self-tapping tee. It's a corpse saddle. Excuse me.
corpse saddle. So the hot tap basically stops us. We don't have to shut down the entire block of the established water main through this. So we're adding a new service connection in a place that potentially didn't have one, or we're replacing one, or what have you. And that tapping saddle or tapping device that they have there goes through, cuts out a coupon, holds the coupon, removes it as it comes through, and you could see water is released right away when he's doing that process there. So the industry itself, each of the thread and the taper of the saddle or the insert, the brass connector, it varies based on, which municipality wants to have that. But our industry itself has now created those fittings, as you heard earlier in the electrofusion discussion and demonstration, that you have every option for you depending upon what taper or what saddle you want to use. So pretty cool process through this. And yeah, it might have gotten a little wet, but we didn't have to shut everybody down there, Pete.
Yeah, I love this one. And then here you can see a completed one. So this is a 1-inch polyethylene service line. And when he made that connection, this connection is a compression fitting. So you have to put an insert stiffener in the polyethylene, then stick it into the female of the compression fitting at the upper end of the outlet. This is considered a best practice. Certainly, we want to see you use electrofusion to connect to the main. I encourage you all to ask questions on this right now. We always, between this and bead removal, this really gets us a lot of questions. So this is an Integrity Corporation saddle. This was a hot tap to a 1-inch polyethylene service line. So not certainly, I mean, this is one of the 8 methods of plowing, installing polyethylene, but plow-in is reserved for rural communities, conduits, water lines, and oil and gas industry puts a lot of these in, and so does the gas industry. But the really wonderful thing about polyethylene is, you can lay it on the road, you can bend it 180 degrees as it goes into the machine, and then it gets plowed in. Here we have a plowing machine with a 12-inch polyethylene line. As it's going in the northerly direction, it's laying the pipe in. Here's the tine that is running the polyethylene in. Ellingson Company out of Minneapolis makes these machines. Really quite wonderful. Here's Ellingson putting in a 6-inch medium density gas line, a 2-inch telecommunication conduit, tracer wire, and caution tape, all at the same time.
Please make sure you know where your other utilities are in this application.
Thanks, Richard. All right, here we have the granddaddy of all the machines. This is ITC out of Calgary, close to you, Richard. This one will do 24-inch diameter down to a depth of 10 feet. This is a dumb machine. It's got a wire rope connecting it to basically 2 Caterpillar D9s that are pulling on it to create the energy that will dig into the soil. But this is quite a undertaking.
The Spotter plow is capable of cutting depths up to 10 feet using its unique ripper tine design.
That's catching the audio now, Pete. That's
good. The winch crawler system, the highest force mobile winch available in the world. After anchoring itself, the winch pulls the plow forward, allowing efficient installation of pipes from 6 to 24 inches. and an array of fiber optic and high voltage cable combinations via the plow's purpose-built installation chute. Unlike conventional open trench systems, the narrow pipe and cable bed created by the plow is closed quickly and can be compacted almost immediately after the machine is passed. No open trench is exposed and subsoils are not mixed with topsoils, providing a clear safety and environmental advantage over traditional trenching.
Pretty exciting. We don't show this video very often, so I was happy to show it
The
today.
spot
So when we were doing that electrofusion saddle demo that we shot, Chris Waite was kind enough to hop in the excavator, and he let me do a fusion. This is 8-inch, and you can see a fusion right here. And I've heard for years, you guys, that guys run over polyethylene pipe strings with Caterpillar tractors and with excavators, and there's never any damage. Obviously not ideal, but I wanted to show you what happens.
There's definitely not a spec for that, Pete. Yeah, that's not the squeeze off tool that we've shown you, but it just the video really shows the ruggedness and durability of HDPE through this process. We would see some type of deformation would be a discoloration of the HDPE. That would show that we've bent that pipe beyond yield. You could see here they went right over a joint through that process. And quite frankly, a lot of cowboy contractors out there do all sorts of different stuff, as you've seen from the mining video and from this video. And it still shows the true ruggedness and durability of HDPE through this. So if we're going to use this pipe material for the hard stuff, such as horizontal directional drill, compressive fit, slip lining, we should be able to use it for the easy stuff as well. And your poll showed us that a lot of you are doing that from open cut construction standpoint. So great videos, Pete. Really, really job well done.
Yeah, thank you, Alan. We're not saying that's okay to do. We're just saying that it does happen, and the polyethylene is probably no worse for the wear, but technically, because you're not following TN 54 rules, you probably ought to cut that section out. This comes from our friends, the Waga brand manager at George Fisher, to demonstrate that if you are going to use a mechanical coupler on polyethylene, like the multi-joint product family, you can use it in good conscience with polyethylene. You just have to use an insert stiffener. I love this video. So what they're trying to prove is, hey, we're fully pressure rated, guys. And if you're going to get a failure, it's not going to be because of our mechanical connection to the polyethylene. So notice that the coupler does not fall off the polyethylene. So the pipe fails before the coupler falls off. The pipe does not come out of the coupler. The pipe just fails. Richard.
And it's ductile. Beautiful ductile failures.
All right, Alan, tell us what's going on here.
All right, so it's very common in potable water systems to be able to try to purge any contaminants within that pipeline prior to turning it into service. So what we do is we simply use a foam pig and then pressurized water behind it to push that foam pig through that pipeline as we see it here. That does not scratch or damage the interior of the pipe, and we're getting any cuttings that may very well have been retained within it. Very common to do this with chlorinated water as well once we're turning it back on, and pretty simple as long as we make sure we retain the foam pig. We don't want to lose that sucker.
All right, now we're moving into some
Compressed-fit
methods.
HDPE lining was developed by British Gas.
So now we're moving into some methods to finish out. We've got about 10 minutes left. The first one is compression fit.
Compressed-fit HDPE lining was developed by British Gas that spans a history of over 30 years. Murphy Pipeline's president, Andy Mayer, worked for British Gas during the development years. For this project, 1,800 feet will be installed in one continuous pull. But fusion joining of polyethylene pipe requires that the mating surfaces are square to each other and properly prepared. The surfaces are simultaneously heated and melted with a hot plate heater and held under pressure. As the molten surfaces are pressed together, the melted ends mix. And once cooled, they fuse into a permanent monolithic joint, which is as strong or stronger than the pipe itself in both tensile and pressure properties. HDPE pipe is an inert material that will never corrode, offers a superior long-term design life of 100+ years, can handle surge events 2 times its operating pressure rating. The HDPE pipe string is pulled on pipe rollers until all 1,800 feet of pipe is fused. While the HDPE pipe is being fused, the host pipe is inspected either by man entry or CCTV. This confirms location and degree of bends, including identifying any obstructions. Next, the host pipe is cleaned. For cast iron pipe, metal scrapers followed by a rubber pull-through are used. Finally, a gauging pig is sent through the hose pipe. Rods are shuttled through the hose pipe 1,800 feet until they come out in the insertion pit. This project, as the cast iron hose pipe ID is 30 inches, an HDPE pipe with an outside diameter of 32 inches is installed.
Okay, right here you see there was a fusion there. That bead has been removed. You can imagine on 1,800 feet, 1,800 divided by 50, whatever that is, you end up with, just under 40 potential fusions. You get a lot of beads building up there, and you don't want that'll impair the ability of the machinery to pull through the die. But once again, this is a 32-inch polyethylene going inside a 30-inch cast iron. That's vegetable oil. This is the pull head, and they already proved out the ID, so they know it's going to fit. Really, really impressive technology. Here's one at Tucson Water. Alan and I have been talking and working a lot with slip linings of this type of failing concrete. Alan, tell us a little bit about this project.
So what this project is a real repurposing. It was really cool to me. This PCCP, pre-stressed concrete cylinder pipe, had been failing since the early 2000s, and it had done so through excessive leaks or otherwise. And now they repurposed this main by pulling in a new HDPE in a slip line fashion, and it provided 10 mgd of new water conveyance for a brand new potable water supply in Tucson area. So this pre-stressed concrete cylinder pipe can fail pretty catastrophically, and here it is. They repurposed it. So go ahead, show us.
So here we are fusing the mandrel onto the pipe string. So this will be right in the front end of the slip line. And it's just a normal fusion, and it takes all the pressure of that full pipe string and it pulls it through. These guys were generally doing between 400 and 600 foot slip lines. This is a mandrel going through to prove out that the ID in fact is what we think it is, so that the slip lining will work. And every inch of that pipeline has to have its interior dimensions proved out. This is really pretty fascinating. This is a slip line that had an 8-foot offset, and we are trying to determine, we're trying to actually get it to navigate that offset in a slip line without using any fittings. That's a gas line that we're going under. Look at that offset. You just bend the pipe. That's so fascinating. Richard?
Yeah, and for that, whenever you go through these processes, a lot of the contractors know that they will have to let that pipe relax for a little bit. let it kind of settle down into its normal temperature under the ground and everything, especially if the pipe has been sitting above ground, it could expand. Just, leaving it. PPI likes the 24-hour, but that viscoelastic response typically occurs within the first 4 or 5 hours. But we want to have that response to this, because you don't want to have a whole bunch of tension or compression on that fitting when you put it on there. Most of the fittings are designed, as you saw in that burst test, to handle that type of that pullout, but it just makes that pipe in a more steady state. So 24 hours is recommended.
Good, thank you. So that's Tucson Water. We have B&F Contracting to thank. We're going to move on here, and we can listen to John some other time, but he's a real master in using polyethylene. We thank Mike James and John Mohan from ISCO for getting us out on the job site. Here's one. Canal conversions are becoming a big market opportunity for the Alliance, because we're making, in the industry, because we're making pipe in up to 11 feet diameter in pressure pipe. So we're competing with very large diameter Hobos and steel, and we're taking canals that lose 40% of their water, and we're putting in thin wall polyethylene pipe. Generally, we don't need thick because it's typically not pressurized. And we're converting canals from open ditch to polyethylene. Sometimes they're left at grade, exposed to the sun, and other times they're buried, like this example. I thank Darren Predmore with Corin, Maine, for getting us out on the job site on this case. I had Adrian Hanan. Richard and I talked to Adrian. We got to know Adrian through Jeff Lohr at ISCO AH up in Vancouver. And Adrian talked about some pretty exciting things he was doing with polyethylene on my podcast from 2 months ago. But look at, Richard, tell us what's going on with this outfall.
Yeah, first of all, Adrian really knows how to push the limits. So he has outfalls that he has to deal with up in the Arctic and Alaska. And what happened with this particular one, those collars you see on the outside are actually concrete collars or steel collars. I can't remember what they were, Pete. But he's filled it full of air to lift it up, because the whole pipeline had literally stuck to the bottom of the ice. So he wanted to release it from the bottom of the ice so he could resink it down to the bottom. And he does this all over the place, where he calculates his buoyancies of the pipe with those concrete collars, and then he will fill it full of water, and they will sink down to the bottom of the ocean floor, where they'll be perfectly safe. So if he ever wanted to do maintenance on it, he could lift them up. But he really does push the limits of polyethylene in terms of its ductility and how it operates. And it's been a very, very helpful application for a lot of the municipalities, either for water draw or for cooling or for condensing or whatever they wanted to do to draw that water in and put it back. So it's pretty impressive.
Yeah. All right. With that, I think we need to wrap it up, because we're at the end of our 75 minutes. Alan, could you tell us how to get our PDHs and CEUs?
Absolutely. At the close of this webinar, there'll be a survey that pops up on your screen. Don't click away. It's going to be the easiest way for us to be able to provide you with the CEUs or PDHs that you need based on your state and your particular continuing education needs. So that survey contains that information for us. You can also contact us. Any of the contacts that you saw earlier in the presentation as well. We tried to put as many possible videos and images up here for you. Remember, we have a YouTube channel that has a lot of more in detail about your particular question discussions. We can't always get to everything. Thrust restraint was certainly one that was important in the fall that we did with ASCE as well. So we do lots and lots of education, and those tools and resources available to you. We also love to talk about polyethylene pipe projects. So if you want to talk about it with us, send it to info@pepipe.org, dlandia@pepipe.org, any of us that way, and we'll be able to talk about your particular project that you've got going on. That'll be the in-person seminar, or not in-person, but virtual seminars, and all the ongoings that we have constantly that tell you what we need here. So any other last words, Pete?
No, that's it. I just want to thank our audience for participating, putting up with us with our sound issues. And our special guest, Richard Colosso, you're awesome. Thanks again for helping me.
Thank you, guys. Thank you, everybody. Really appreciate it.
All right, stay tuned.
Thank you.